whether they want to do it or not. For people who do it, I would take the maximum of the 2 exam ones. So I'm not going to do the average thing. It's going to be just the maximum, which means I'm going to have to grade the first. I'm going to have to grade exam 1 and also exam 1.1 in order to come up with the maximum, which also means it's going to take a while to get it done. Alrighty. The first, okay, so in exam 1, there were some phrasing of questions that a significant amount of people did not understand. And I felt, okay, so this has nothing to do with what people tell me. This is me coming to the conclusion that go like, yeah, maybe that's possible, and maybe I should give you guys a second exam or first exam. I know it's confusing. Exam 1.1, just so that part is no longer an issue. So if you guys have not watched the YouTube, I actually posted a few recordings of the answers to the exam on last Wednesday. So that's already on YouTube. So obviously, I am not going to ask exactly the same questions. I mean, what would be the point? What would be blah 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 blah? What would be the point of asking the same questions when the key is already on the internet on YouTube? Right? So no, it's not going to be the same. It's going to have at least some new elements. So you can count on that. But I can promise you there won't be another exam 1 makeup. This is it. Okay, so 2 is enough. All right. Yeah, about that. Now you guys do realize that when you work in industry, it's going to be kind of like this, except your paycheck depends on it every day. I'm not trying to scare people. I'm just saying that I was a supervisor / manager once, and yeah, it's kind of like this. Every day, problem solving, debugging under pressure. Things need to be done like a week before, not yesterday. Yeah, and then marketing and sales will be breathing down your neck and say, we promised people that we would have released this product 2 weeks ago. Where is it now? And then your boss is gonna ask, yeah, so what is happening to your team? How come you guys are not, finishing the product yet? I'm speaking from experience. So, all right. If you guys want to get your grade from the first exam first, it's gonna be a little bit of time. Because as you might have noticed, all the questions are open-ended, which means it's not going to be grading is going to be all manual. It's not just going to be something where I can just match things up, because I'm going to look at the explanations and whatnot too. So I would probably do it before giving you the result of exam 1. You can always do both, right? I mean, you can always do both, and then whichever one ends up with a higher score, that's going to be your score for exam 1. So there is that. Alrighty. I have not decided on when the makeup is going to be because it's going to take me time to get it ready. So I would say at least it's 1 week out. So that's about it. Any other questions? So for people who feel really, really confident about the first exam, they don't have to take the second one, but I think it doesn't hurt to take the second one either, because everybody is going to potentially get a higher score. I cannot guarantee it. Okay, this part I cannot guarantee, but I think everybody would be able to get a higher score, just because certain elements would be familiar, but I'm not going to keep everything the same. So there will be some variable between the 2 exams. And I will try my best to not to make it confusingly similar, which is also something that I apparently, am very good at, is making things similar, but so much that it is confusing. Yep, you're welcome. It is definitely extra work, but I think it is fair, okay, if some people say that some of the phrasing, is a little bit foreign in this class. And I can understand that too. Alright. Alright, so getting back to section 7 of the test. Daria, no, I'm not going to give you a link because I think you guys know where to find YouTube and where to find my channel. So it's really just my channel. Some profs on YouTube, and just go to the recorded portion, and the videos are all titled, accordingly. So you should be able to find it. That's it, Dalton. I forgot about that too. I put all the links into the channel and then I forgot completely about it. Yes, yes. So read all the channels. Yes, all the traffic is important. There we go. All right. I think we're getting back to updating the playlist. Okay, that'll work. Section 7. All right, getting back to section 7 again. Total ordering. Total ordering is the same as partial ordering, except there's one more requirement, which is this one over here. R is comparable over X, meaning that for all E and F in X, ERF or FRE, this is also called the Trichotomy Law. Alright, so if this stuff here looks really kind of foreign, like what exactly is reflexive, what exactly is antisymmetric, what exactly is transitive, what is partial ordering? Well, that is an indicator that some people might need to review the content, because that's stuff that we have talked about prior to the exam. Alright, so the only thing added to partial ordering for total ordering is really just this last item here. And this is the most concise way to describe it. If you pick any elements from X, just one is called E and one is called F. Now remember, E and F are variables, okay? They are really just ways so that we can refer to what did you pick as E and what did you pick as F, okay? So they're basically variables, but they can be the same element in X. And what we want is ERF or FRE. So that means it has to relate one way or another. Cannot be missing both at the same time. Okay, so as long as this requirement is met, then the relation is called comparable over R. This is also this is also called the trichotomy law. And with this extra requirement met, then the relation is no longer partial ordering. If it only meets the first 3 requirements, it is called partial. But if it meets all 4 requirements, it is called total ordering. And total ordering is important because if you want to sort an array, then you need the values of the array in relation to whatever comparison you're going to use. It has to be a total order. Cannot be a partial order. Has to be a total order. So the natural comparison operator that we know of, being less than or equal to or greater than or equal to, those are both total ordering type of relations. So every time you want to think about, okay, what exactly is total ordering, you have these 2 examples: less than or equal to for any numerical value, and then greater than or equal to for, okay, I'll just make it more restrictive, for real numbers, because complex numbers cannot, doesn't have the same kind of ordering. So you can only apply that to real numbers or rational numbers. No, irrational numbers. There we go. All right. So are there any questions about relations? Alrighty, so looks like we don't have any more questions about relations. Alright. If there are no questions about relations, we're going to move on to a new topic. This is a new module, both in terms of what I write as well as the organization in Canvas. Alright, so exam 1 score is not going to be there for a while. Because I will be focusing all my energy to exam 1.1, so that way hopefully it will be done before you guys have completely forgotten all the stuff that you have learned up to and including what was that again? Functions. Now trust me, you won't, because those things are going to be needed later on, so we're going to have to get back to some of those topics once in a while. All right, so this is the new topic. It has its own module in Canvas as well as its own module in terms of what I write. And this is a module that can be confusing or difficult to understand or abstract. Now, I do have one thing to say about this class being abstract. It is supposed to. I mean, it really is supposed to be a class that is abstract. Because math, generally speaking, is an abstraction of stuff, right? Because it's even compared to physics, math is more abstract because this is a tool. It's a language and a tool as well that allows us to kind of reason things out, not only in computer science but also in other natural sciences. So there is definitely that abstract element to this class, which means for certain people, you might want to think in examples. So you can use examples to ask questions. You can ask me for examples, but examples would be helpful, for people who learn by examples. All right. So what we'll do now is to get started with propositional logic. So I'm going to start with section 2. So propositional logic itself is much older, much older compared to computer science. It has been around for a long time. So what we'll do is we are going to talk about general propositional logic, what it is about, and how most people use it until computer science came along. And then what we'll do is to say, okay, so with computer science, okay, with computers, with mechanical ways of doing computation, what would be new to that? How would that change the way we look at propositional logic? So propositional logic is about proving theorems. I'm not sure how many of you really like to prove theorems in your math classes, because all of you will need to take calculus 2, to get your computer science degree. So you do have to take certain math classes, and certain math classes like linear algebra typically involve some kind of proofs. All right. Well, so don't think about this as proofs. Think about this as how to debug a program, because when you're debugging a program, you are also applying logic, and you are actually trying to prove something when you're debugging a program, because in the process of locating a bug, you can think about this, okay? You can think of it this way. The actual bug in a program, the defect in a program, is what you're trying to prove. So the question is, how do you locate it and how do you link it all the way back to, oh, okay, so on this line here, I should have used less than, but not less than or equal to. Obviously, I'm using that as an example. But the question is, how do you find that flaw in the program that's causing the program to misbehave? It's applying logic, okay? So, and also, I'm assuming all of you are transferring to a 4-year university. There are at least 2 upper division computer science classes that are math based. So basically, those 2 classes are all about math. They look at computers as what we call automata or automaton, as a singular noun, and it's all about mathematical proofs. The truth is, computer science really is a branch of math. It may not look like it, may not taste like it, but it is. So eventually, we're going to run up against, the kind of reasoning that we are going to describe in these classes. All right, so general propositional logic, back to here. So general propositional logic is a calculus. It's a 4 tuple. So all that means is there are 4 components to propositional calculus. Okay, there are 4 components. The first component is called alpha. You can call this A, but it really is the Greek letter alpha, uppercase. Alpha is a set of symbols to be used, and symbols have no inherent meanings. So typically what we do is we use 0 as false, or at least in this class, I use 0 as false, 1 as true. But remember, it has no meaning. So 0 is just a symbol, so is 1. And then we have some English alphabet letters like PQRST, and then we have some Greek letters like psi, phi, theta, and so on. So at this point, all we do is to look at all the symbols in alpha, as I said, as the most basic components that we're going to use to express stuff. Okay, what stuff are we talking about? We'll get to that later. So that's alpha. Uppercase omega is a set of operators, and if you talk to mathematicians, they call these connectives. So calculus is basically just a system of manipulating symbols. You can kind of look at calculus in that sense. Let me see if I can look up a broad or general definition of calculus in this case. Because calculus is not limited to just the calculus system that we normally refer to. So in a more general description, a calculus is a particular method or system of calculation or reasoning. Let me pull this window into view so you can see it. So when we look at propositional calculus, we are using the second definition of calculus. It is a particular method or system of calculation or reasoning. So in other words, we're talking about a system here, which consists of its own language and also its own operations. So is that okay? That's a good question. This is basically just a symbol for a calculus, for a propositional calculus system. So this one here is really just a name, so you can have L1, L2, L3 to refer to different systems. That's basically all it is. It is just a name. All right, we got two more people still typing. Okay. Laplace transformation. Do the connectives contain set operations and set operators and Boolean operators? Okay, so so it's a way of the marketing system. Okay, I'll give you guys some examples later on. So right now, all we have to do is to understand that omega are operators. So typically, if you're talking about a traditional logic, then we have conjunction, disjunction, negation, implication, equivalence. Those, all the things that we talked about in week 1 of this class, they would belong to omega. So I hope that helps to clarify in a normal, common propositional calculus system, what omega is going to consist of. Okay. Yeah, I can give you guys an example later on, using my notes, which is currently empty, but I'm gonna put something here after I talk about those letters. Then I will show you some examples. All right, so alpha, omega, and now we are moving on to zeta or zeta. So zeta is a set of transformation rules. More on this later, because this specifies what we can do with things. Okay, so these are specifying operations. Omega actually, interestingly, does not specify operations. It's nothing more than a symbol that can connect other symbols. That's basically, and in a hierarchical way, so I'll describe it later on as well. And then we have iota. This looks like uppercase I, but it's actually uppercase iota. Iota is a set of well-formed formulae that are known to be true. In other words, you don't ask me why those things are true, because I just say they are just true to begin with. So those are axiomatic things or expressions that are known to be true. All right, so now is a good time to give you guys an example of what a propositional calculus system may look like. Okay, and this is going to be something that this is what most people understand. What propositional calculus is, and then later on we'll look at it from a different perspective of okay, so this is a little weird, but there's a reason why it is a little weird. All right, so I'm going to give you an example. I will be typing on the right hand side. I'm putting it here just so that you guys don't feel too bored, because nothing seems to be happening on the screen. All right, so I'm going to give you alpha, can be defined as 0, 1, and then we have p, q, whoops, p, q, r, s, t, and then I can use some Greek letters like psi, phi, theta, and typically three, ish, is enough, but this is just an example, okay? So now I just defined my alpha to consist of what we see as 0 p q r, 0 1 p q r s t, psi, phi, and theta. So right now these things have no meaning, okay? They're completely meaningless, okay? They are just symbols, just things they can type on the keyboard, so to speak. Next, we're going to take a look at omega. So this is uppercase omega, and let me open it with a $sign first. So omega can be defined, if this is a normal reasoning kind of propositional calculus system, then it consists of all the operators that we have talked about. We have OR. It will look like an OR and an AND later on. We have logical negation. And if you want to, you can also use implication and also equivalence. Like so. There we go. So it's not really that big of a deal. No, we are not dealing with sets. Okay, we are only dealing with truth, values of true and false, or Boolean values. So there's no such concept of set in this particular calculus system. Now, obviously, you can define one where it can take care of concepts of sets. Okay, but I'm not going to use that as an example. Alright, so now the next concept that we need to introduce is not so much the other two items or the two components, the other two components in a propositional calculus system, which is transformation and also iota. So what we want to talk about now is WFF. Okay, nope, it's not WTF, it is WFF, which stands for well-formed formulae or formula, depending on whether you want it to be formula. There we go. We'll get to it. We'll get to it. These are the most basic concepts. So we are gradually building up, on the whole concept of what is propositional calculus. So one thing you have to keep in mind all the time is propositional calculus is supposed to be mechanical. Okay, you don't need to understand, oh, this symbol here, it means OR, and the truth table of OR looks like this, and it makes sense because in English, this or whatever natural language you're familiar with, it means this. Okay, this is and, it means this. This is not, it means this. No. All of these are nothing more than just symbols. Okay, they're all just symbols. At this point, they make there's no difference. In terms of how one is differentiated from the other one. It is when we get to the transformation rules that we'll say, oh, okay, so it does make a difference in which operator we are using because different rules apply differently to these different symbols. Alright, so what symbols do we use to define a propositional logic system? It's the funny looking L that we saw earlier. Okay, so when we use, oh, not this one, let me close that first. Alright, I think it's this one. So this thing here, this is actually the symbol defining a specific propositional logic system. And then these are the components. So we are basically just describing the four components to any propositional logic system. And I'm not sure what the left arrow is doing. It's the reverse of implies, right? You can call it implied by. So you can, if it's really just the opposite direction. I normally do not use that symbol because it just adds to confusion unnecessarily. Alright, okay. So now we're getting to what is a well-formed formula, okay? So the way we define it is going to be recursive. Okay, so every individual element from alpha is automatically a well-formed formula. So in the notes, I use a predicate. So if you see this part here, I use a predicate, and the predicate is a WFF. So this particular predicate is true if and only if whatever it is, whatever you pass to it, is actually in fact a well-formed formula. This particular sentence here is confirming it doesn't matter what you choose out of alpha, every element in alpha is by definition automatically a well-formed formula. Alright, so do we have any questions about this particular statement here? Every individual element from alpha is by definition a well-formed formula. So I'm just going to pause and make sure that everybody understand this, what I mean by that. And I can relate to you using the example. Remember what I said a little bit earlier? All of these concepts are abstract, but in order to quote unquote de-abstract this, I can now claim and say 0 is a well-formed formula. I can claim, well, let's see, theta is a well-formed formula, and so on. So every single element that I put into alpha is a well-formed formula. Alright, so let me go back to the text channel. It's the other way around, Elijah. Everything in I is a well-formed formula. So when we get to I, we'll get to it. Okay, but right now, we just want to define what is a well-formed formula, starting with the ground rules. That is the basis where we build larger and larger items. No, I is not necessarily a subset of alpha. Iota is not necessarily a subset of alpha. We'll see, okay? Because I cannot talk about that until we are done with the definition of well-formed formula. So these are all good questions, but I cannot answer those questions until I present and explain what a well-formed formula is. Then we can move ahead and define what is in iota and what is the relationship between iota, well-formed formulae, and also alpha. Yeah, that's fine. It's good. It's a good idea to ask those questions, but I just want to tell you guys that I cannot answer those questions until I have defined what is well-formed. What is a well-formed formula, which is basically just an expression. So at this point, I want to focus on just this part here. Does everybody understand what I mean when I say every element of alpha is automatically a well-formed formula by itself? All right, excellent. So now we can move on to the recursive part. Okay. So the recursive part is saying something kind of like this. Okay. So we can say for all. And this time I'm going to use a different symbol. It's conventional to use a Greek symbol in this case. So I'm going to use psi and phi. And then I can say I can now use what I have defined earlier, which is a well-formed formula. So math TT is a well-formed formula. And then we have a wedge. Math TT is a well-formed formula. And this time apply that to phi. And then we have a right arrow, which is implication. Implies. Oh, I forgot one more operator thing. Alright, so let me stop it here first. It's not done yet, so it's okay for this to be in red. So one more thing about omega that is helpful is omega itself can be divided into a bunch of subsets. So let me explain that first. Omega subscript I is a set of operators that require I operands. Alright. Alright, so I'm going back to re-explain, the components of omega. So omega can have omega 1, omega 2, and we don't have omega 3 because we don't typically use operators that require 3 operands. So in this case, it is not unusual that omega 1 is a set that only contains the only operator that requires just one single operand, which is logical negation. You cannot see all notes. Okay. And then omega 2, I'm just looking at the, yeah, you should be able to see enough. Omega 2. Oh, yeah, that part is not done yet, so no worries. I'm not done with that portion yet. So omega 2 would be the set of all the operators that require 2 operands. And with 2 operands, everything else needs 2 operands, right? Or has 2 operands and has 2 operands. Implies has 2 operands, and then if and only if, or equivalence, also has 2 operands. So we're going to include those guys. Okay, so there's a V, there's a wedge, there is a right arrow, and then there's also a left right arrow. There we go. Alright, so with this defined, I can now get back to this definition, and so I can add to it. And I know it doesn't it's difficult to read it right now, but I'm just gonna work on that a little bit. Okay, so now we have to say for all, oops, for all, oh, 2 double slashes. Alright, for all, and then we pick one operator. Okay, so we pick operator O in, and this time we make it clear this is omega 2. So so O is going to be an omega, it's going to be an operator that requires 2 operands. And now we can go all the way down to here to say it implies is, oops, math TT is a well-formed formula. The question is, what is a well-formed formula in this case? And that's going to be just psi, whatever OP is, or the operator is, and then we have psi and phi on this side. Close that. Close. Close. Okay, I'm not sure this is. It's still complaining. It's in red. So let me find out why it's complaining. Yeah, it looks that way. I'm just gonna take a look. Oh, I can see it. The math TT has an open paren instead of an open brace. There we go. Alright, so there's one. And then here's the other one. There we go. That looks good. I'm just matching parentheses now. One too many close parentheses. There we go. Alright. Yes, omega 2 has 4 items in the usual way that we use propositional logic. Yes, so omega is a superset, or omega is the union of all the omega i's. So the set of omega without a subscript is the set of all operators. So it consists of these subsets. Okay, omega 1, it would be the subset of operators that only require one operand. Omega 2 would be the subset that consists of operators that require 2 operands, and so on. That is a lowercase o, because this is a lowercase o right here. This is lowercase o, and this is referring to the same lowercase o. Yep. All right. Sure. Let's take row. Okay. Alright, so row taking activity for today is right here. I'm gonna release it now. The word is okay. I need to double check because sometimes I think I have changed it and then I forget to click update question and it doesn't count. Yep. So the word is peace. P-E-A-C-E, all lowercase. Just copy and paste it. There we go. I think that we are missing one more. Oh, there we go. Alright, so I think I'm missing one close parenthesis, so I gotta close one more time. There we go. Yeah, I think so. It's up to you. I mean, how you guys want to interpret, the context in which peace is applied is up to you. Generally speaking, if you look at the pay, that's usually proportional to the difficulty of the field. Not always. There are some low-paying jobs that are also difficult, but typically the higher the pay, the more difficult those jobs are, unless that's something that you like to do. Now, when it is something that you like to do, it doesn't make it any easier. Okay, it's just that it's more enjoyable, so you kind of not feel the difficulty as much. So there is that. Because I don't want you guys to go in, after getting your bachelor's degree and just, kind of think, well, I got my bachelor's degree from a certain CSU and I have a GP of this. I think I'm guaranteed a job that is paid this much money. That is not true. That is not true. It's interesting. If you look up the statistics, you can actually find it. So this is not just me saying it. If you look up the statistics, in a computer science engineering field or related field, there's a high demand. There's a sharp increase of people. How do I put it? The job market is there, but at the same time, there's a certain percentage of unemployment. So it doesn't make sense, right? It does make sense when you reason it out because the people who are unemployed, even though they might have a degree or GPA, they still cannot find a job because they are ultimately not employed by any employer. And that's the bottom line. Yes, Chris, I'm afraid that you have been lied to. See, before Stack Overflow, we had these textbooks called Idiot's Guide to Blah 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 Programming, or learning blah 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 programming in 24 hours or something like that, and they usually come with a CD-ROM. Yes, I know some of you are way too young to know what a CD-ROM is, but some of those books come with a CD-ROM. And in about year 2000, there were a lot of people learning how to do web scripting using those CD-ROM scripts. So they just copy and paste, look up the right section, copy and paste, look up the right section, copy and paste. And as it turns out, some of that code is susceptible to SQL injection attacks. And as a result, people know, the first thing they try is a few things, because they know a lot of people were applying these copy and paste from those textbooks. So And they found that there are a lot of websites that are susceptible to these SQL injection attacks, because whoever wrote that script was just copying and pasting from the textbook, or copying and pasting from other scripts that other people also copy and paste from the textbook. Yep. Yeah, so that's how some of the websites are susceptible to SQL injection attack. It's not the server itself that is susceptible. The server can be totally secure. It's the script that is susceptible to SQL injection attack. Yeah, fun time, fun time. And as you probably have heard from other people, if you're too young to remember this, the dot-com boom, which basically ended in around 1999 or 2000, depending on how you count the end of the boom, it came the bust. Okay, and once the bust started, there were like 5 or 6 years where computer science, all the jobs related to computer science, were in the dump. Nobody wanted to sign up for computer science classes. Yeah, I was teaching what was equivalent to CISP440 at right now. I have a class of 3 students. Yeah, it was that bad. Okay, I'm just reading the comic strip here. Oh, that's funny. But these days we like to encrypt the data and then ask for ransom. Alrighty, getting back to the main topic here. Actually, what Chris just posted here has a lot to do with what we are talking about right here. Okay, about proving theorems. So I'll get back to that topic in just a little bit. Okay, but I do want to just kind of talk about this part here. So what is this saying? Okay, so let's go back to this expression here. And I'm really hoping that by the end of this semester, hopefully way before the end of this semester, people are going to start feeling comfortable reading notations like this. Okay, because this is concise, and this is also precise from the perspective of mathematics. So this is basically saying, give me a psi, give me a phi, and also give me a lowercase o. The restrictions is that O has to be coming from omega 2 of some propositional logic system. So what we know about O, lowercase o, is we don't know what it is, but we know it is an operator that takes 2 operands. Okay, so that's the one thing that we know about O going forward. What about psi and phi? Well, I didn't say anything about this part here, but all I'm saying here is if psi is a well-formed formula, and phi is also a well-formed formula, then we know that the resulting expression of psi o phi is also going to be a well-formed formula. That's it. Okay. So, do we have any questions about this notation? Obviously, I'm going to use some examples later on, but I want you guys to think about it first before I get to the examples, because ultimately I want you to be able to read this kind of expression and understand what it is. But I can use some examples to illustrate, and also to point out, if someone might have misunderstood it, then the examples will help point that out. Alright, so this symbol is for all, so we can say for all psi and phi. For all lowercase o, that is a 2 operand operator. If we know that psi is a well-formed formula and phi is a well-formed formula, then the truth value of this conjunction implies that if you use an operator that needs 2 operands, on one side we have psi, on the other side we have phi, then that entire expression is also a well-formed formula. So I just kind of retranslated this statement in English. Alright, so Enzo said, is saying psi or phi is a well-formed formula It's not WWF, it is WFF. Well-formed formula ensure it is in the set of alpha. Nope, nope. This is beyond alpha, right? Because there's no mentioning here. Okay, let me go back to here. So there's no mentioning in this entire thing that mentions anything about alpha. All this says is if psi is a well-formed formula and phi is a well-formed formula, then whatever expression you come up with using psi, phi, and a two operand operator O, which we locked down here, that expression is also going to be a well-formed formula. It's a recursive definition. All right, so let me read what Danny just typed. That part you have highlighted right now is that using the notation for a relation. Nope, this has nothing to do with relation. This has to do with how is a well-formed formula is defined. So let me just add one more thing. I think that was in the notes too. So how do I capture the fact that everything in alpha is automatically well-formed? So I'm going to just add this part here. So that part we can just say for all E, in alpha. So if you choose anything in alpha, that is automatically a well-formed formula. So now we say math TT is a well-formed formula, and then we use E as the operand, and then close that, and then close that. There we go. Which I believe is exactly what you see in the module itself. So this says every element in alpha is a well-formed formula. There we go. Okay, so is the cardinality of the set of WFF containing only psi, phi, and omega? Nope, it's actually okay, it depends. Okay, it depends on what is in your omega, because things can nest. Okay, so let me illustrate what I mean by things can nest. Alright, so I'm just going to point out a few things that are probably pretty clear to all of you at this point. So P is a well-formed formula. Okay, any argument about that? I mean using what we have in alpha and what we have in omega, I can say that lowercase p is a well-formed formula because it is an element of alpha to begin with. Is that okay? Alright, cool. So now I'm going to present something else that is also a well-formed formula. So I'm going to say P wedge and P is a well-formed formula. Would that be okay? Well, let's think about this, right? So and, okay, this wedge symbol here is an element of omega 2, right? Okay, yes, it is right here. And then we look at P and ask, well, we need everything, we need all the operands to be well-formed in order for the expression to be well-formed. So we look at P and go like, is P well-formed? Yes, P is well-formed because it is a part of alpha. And we look at the other side, it's like, oh, that's a stupid question because it's asking the same thing. Yes, P is well-formed. So now we have two well-formed formulae as operands to an operator that requires two operands. And according to this second rule, the composition, which in this case, psi is P, O is conjunction, and then phi is also P in this specific instance. Yes, so then we can conclude that P and P is well formed. Are we doing okay so far? Because this is the step where we can build larger and larger things. All right, excellent. So where do we go from here? How about things that are totally redundant? Oh yeah, that's why I use examples, right? So let's check this out. Okay, we have P and P. Oops, P and P, and P and P. Oh, come on. P and P. There we go. It's well formed because we have just established that P and P is well formed, and obviously, if this is well formed, oops, if this is well formed, then so is this because they are exactly the same thing. So once again, we have two well formed formulae that are supplied as operands to an operator that requires two operands, and that makes the new expression also well formed. Are we doing okay so far? Are we kind of understanding how all this stuff is stacking up? So WFF basically means it's a valid statement. It is syntactically correct. That's basically all it means, is that it is syntactically correct. All right, cool. So what about that, one thing in omega 1? How do we take care of the omega 1 thingy? Well, all we have to do is to do this thing, just modify a little bit, right? Because we only got one expression, so we just say this is now in omega 1, and then we specify okay, we don't have the wedge, we don't have phi anymore to speak of because we only got psi in this case. And it depends on how you want to use a single operator. Typically people use a prefix, or I should say, when we use a unary operator, we put it in front of whatever it's supposed to operate on. So that would take care of what happens, what do we do with operators in omega 1? Is simply to say, hey, give me a well-formed formula. If I apply a unary operator on that well-formed formula, then it is also well-formed. The result is also well-formed. All right, so I'm getting back to the text channel. Exactly, so Elijah is correct. So P and nothing is not well-formed, and P is not well-formed. So that's how we determine what is well-formed and what is not. Okay, I'm going to put it in the examples because it's a good example. So I'm going to put Elijah's example into the notes here. So we'll say wedge P is not well-formed. Alright, so getting back to the text channel. If we have one conjunction and the disjunction on second P after 2, okay, I think Mohammed, you might need to type up the entire thing. You don't have to use the math equations, just kind of type it up in the text channel, because otherwise I can't really quite. I can understand what you're saying, but I cannot differentiate, because there are several ways to interpret what you just said. So I just needed to be more specific. So P and X would also be not well formed because X is not in alpha. That is correct. So I'm going to put Luke's example here. So I'm going to say P wedge X is not well formed, and in this case it is because X in alpha is false. All right. And then Danny said, or repeated the question from earlier, and if something is well-formed for one calculus, it may not be well-formed for different calculus. That is correct, because it really boils down to what we choose to be included in alpha and what we choose to be included in omega. Alright, so Mohammed is, that would be well-formed because P disjunction P is well-formed itself. P and P is well-formed, so when you create a new expression combining those two, the result is also well-formed. I can put it in the example. Not P and P is also well-formed. That is correct. So P and negation P is well-formed. So essentially this is a syntax checking. Okay, that's all it is to syntax check to make sure that if you have an operator that needs two things, you're supplying both things. If your operator only expects one thing, you're supplying that just one thing, and so on. So not W would also be not well formed because we did not include W in alpha. That is correct. Because W itself is not well formed. Okay, that's the other way to say it. Okay, so we can say W is not well formed because W is in alpha is false. So there you go. So are we doing okay so far with the concept of what is well formed and what is not well formed? All right, so Elijah says so not P would pass to so phi and psi are placeholders. They're basically just placeholder and go like, okay, if I'm all right, so let's get back to this statement here. This part here is a universal quantifier without any restriction. So at this point, psi can bind to anything, so can phi. It can bind to anything. It has nothing to do with alpha, has nothing to do with omega, has nothing to do with what is well formed. It can be anything. It can be your car. It can be your pet. It can be a germ. It can be a virus, and so on and so forth. So it is without any restriction at this point. But in order for this expression here to have any meaning, this implication here, we better make sure that psi is a well-formed formula under the current propositional calculus system, and the same thing applies to phi. So once we confirm that psi, phi are both well formed, then we can say, and also in addition, we confirm that lowercase o is part of omega 2, then we can conclude that the expression that you end up with by combining psi, phi, and the operator o, that expression is also going to be well formed. It's under the current system. These are part of the example that we are just illustrating right now. So I am using this specific alpha. I'm using this specific omega. So well-formed is a well-formed formula. Really need extra parameters because it depends on what is your alpha and what is your omega. All right. So I'm not going to go check the off-topic thing because it is in off-topic. So I'm continuing to focus on the text channel right now. So are we doing okay so far? So is a well-formed formula is conditional to what we consider as alpha and what we consider as omega, and also in omega what is a single operand, what are our single operand operator, and what are our two or double operand operators. All right. So are we still doing okay? Okay, cool. Excellent. All right. So one thing you can ask yourself is how can you write a subroutine, even if it's in pseudocode, so that if you're given a string, okay, how do you check, or if you're given a expression, how do you check whether that expression is well formed or not? Okay, so kind of think about it a little bit. You don't have to go through all the actual code because parsing is not easy. Okay, but you can kind of think about the process of how to make that work. This sort of feel like designing a class in OOP. Yeah, well, there are certain elements of it. And then Mohammed said, why did they have to go term savvy on it, symbolize? Well, that's because this is a language. Remember, mathematics is, first of all, a language, because it is a way for different people to communicate concepts. And by by having a common understanding of the same set of symbols. So mathematics is first a language. It is a universal language too. So yep, exactly. And I'm hoping that you guys get familiar with this, and then by the time you get to the upper division classes that are also math heavy, then you look at these symbols and go like, yep, we kind of understand the symbol, so you can focus on the concept and not so much on just the mechanism of understanding what the text is trying to say. So there you go. All right. So it looks like we're doing okay in terms of understanding what is a well-formed formula. So now I'm going to ask you a question, and I will present a question in this way. What is the cardinality of a set such that each element in the set, I'm going to use, okay, I'm not going to use one of the Greek letters in alpha. I'm going to pick something else because it doesn't need to be, this is the description of the set itself doesn't need to use a symbol from alpha. So I'm just going to pick something else. Let's see. I'm just going to pick beta, okay? So beta such that math BB is a well-formed formula. B beta. Close that, that. Okay. Oh, that's not what I want. It's not math BB, it's math TT. T for tally type. There we go. All right. So what do you think is the cardinality? I forgot the close vertical bar. Okay. So under the current system, okay, or under the way we currently define alpha and omega, what is the cardinality of the set of all the well-formed formulae? No, it's not going to be 0 because we know that alpha itself is not empty, right? And everything in alpha is automatically well formed. So that means whatever set we are creating right here, this ad hoc set that we are creating right here, it at least has the cardinality of alpha. All right, it's actually infinite. Think about it. Think about the examples that I have been trying to making, right? So P is well formed, P and P is well formed, P and P and P and P is well formed. What is the next one up? If this is a test to see if you can understand what pattern we are progressing with, what would be the next one? The next one is going to be P and P and P and P in parentheses and P and P and P and P in parentheses is also well formed, right? So you can see how this doesn't need to end. I'm just using one symbol from alpha and one operator from omega, and I can generate an infinite number of well-formed formulae. Are they useful? Are they meaningful? No, they are not. But they are all syntactically correct, and that's what counts in order to be a well-formed formula. Alright, so getting back to the text channel. Exactly, we can keep extending any combination. Pick any two things that are well formed to begin with, combine them using one element from omega 2, and you get a new thing that is also well formed. It doesn't mean it's useful or meaningful in any way. It simply means it is syntactically correct. As long as sets of 2. I'm not sure what you mean by as long as sets of 2, Mohammed. That's a very good question. Is it Aleph? No. Is the cardinality Aleph? No. I have not thought of that. I'm just trying to think, is there a quick and easy way to have a bijective function between natural numbers and the well-formed formulae that we can generate using this definition? So the answer is no, I do not know the answer to that yet. I can think about it, but I do not know the answer yet. I think as long as if whatever is in A. I'm not really sure what that means, because A alpha is really just the starting point. From the symbols in alpha, we can create any kind of well-formed formula. Oh, okay, I see. Okay, gotcha. As long as sets of 2, whatever and whatever. Well, we have whatever and whatever, we have whatever or whatever, we have whatever implies whatever, and so on. I mean, I'm only using a very small part of what is in alpha and omega, and you can see I can already generate an infinite number of well-formed formulae. So the point is, okay, the point is the cardinality here is infinite. Now, I'm not really sure whether it's countable, which means, does it map to the set of all natural numbers using a bijective function? That I do not know yet. Okay, I have not attempted to prove that. But we know it is not finite. Okay, that's the whole point. It is not finite. Because that comes in, that's going to be important later on when we talk about how to prove a theorem. Because when you have a set where you do not know, where there's an infinite number of elements, and you're asking, somebody is asking you and go like, okay, I need something, I need a well-formed formula that has these properties. So you're trying to find a needle in a haystack, okay, so to speak, except you don't know, except your haystack has an infinite number of elements, which means you now have a problem, because now you cannot differentiate between the fact that the needle is not in the haystack versus it is in the haystack, you just haven't found it yet. So we'll get back to that little dilemma later on, and we'll find a solution to solve that problem. But for the time being, all we have to do is to say, oh, so why didn't you just tell me that well-formed formula is really just a syntactically correct expression? Yeah, that's basically what it is, except it is called a well-formed formula when people refer to these things in propositional logic. Alright, so let's see what Nathan has gotten here. Okay, let me go back to Danny's question first. Some elements that could be in B. Well, B is not is not a set. Okay, so you can call this B as a set, but this is what I would just call an ad hoc set, where I describe the membership, but I didn't quite describe the name of the set itself. That would not be correct, because conjunction is not going to be a well-formed formula by itself. So conjunction is not in the set itself. Conjunction is an operator. It is in omega 2, which means it is going to be in omega, but it's not going to be in this set, because in order to be in the set that I'm highlighting here, each element has to be a well-formed formula. An operator by itself is not well-formed. Okay, moving on to Nathan's question. So even if we only have alpha having A, omega having negation, then you can still be infinite, because you can have the negation of A, then the negation of the negation of A, then the negation of the negation of the negation of A, and so on. And even that would still be a set that has an infinite number of elements. And in that case, I can say for sure that there's an bijective function mapping that set to the set of all natural numbers. That one is easy, right? Because you only have one degree of freedom, so you just have to count the number of times you apply the negation, and that's an easy way to generate a bijection between the set of natural numbers and that set. Yep. So P by itself is well formed, yes, but elements of omega 2 are not. That is correct. That kind of goes back to the definition, right? It kind of goes back to this definition here. So even when you have, an operator from omega 2, that by itself is not well formed. It is only when it is serving as an operator or a connective. This is why it's called a connective, because it connects to well formed formulae. And that connection, the connected piece, the larger piece, is well formed. Yep, operators need something to operate on. Now, don't ask me what is going to be in omega 0, because you can, in a way, in a very weird way, look at 0 and 1 as omega 0, but let's not go there. Because omega 0 really just boils down to a symbol that, by itself, has a value. But then, if you look at 0 as omega 0 and 1 as omega 0, then 0 and 1 are no longer well formed by themselves. And I guess that's the reason why we don't put 0 and 1 as a omega 0 operator. I don't think omega 0 is a thing. I'm just kind of talking about what if we consider omega 0. What if we consider operators that do not require operands? So without operators, then the set that we are constructing would only have the cardinality of alpha. That would be correct. So what Nathan typed at 112, which is now, is correct. That is correct. Now that would be a very deformed, I wouldn't say deformed, but it would be not a very useful propositional logic system, because there's nothing to prove in that case. Okay, but we haven't gotten to the point of proving theorems yet. So all we want to do is to introduce the term of what is well formed. It simply means it is syntactically correct based on what we have included in alpha and what we have included in omega. So are we good so far? All right, cool. So now we can start to introduce omega first, okay? And someone's going to say, but what about zeta? Yeah, I'm skipping zeta for a reason, okay? Because iota actually is more important, okay? So now we can now introduce what is iota. Okay, so I'm going to use another bullet point here, maybe down here. All right, so iota is going to be a subset EQ, okay, always EQ, of the set that we just constructed. Okay, so beta such that math /math tt is a well-formed formula. Beta and close that, where there we go. All right. So this is, so once again, I'm choosing to explain it using math notations because I want you guys to have more exposure to math notations. So iota has to be a subset of the set of all the well-formed formulae. So that's one thing we need to know, is everything in iota is also well-formed. This is just one way to say that every element in iota is well-formed, because I can now say iota is a subset of the set of all well-formed formulae. But there's one more thing on top of it, is if I choose anything in iota, that expression in iota, that well-formed formula, is known to be true. Don't ask me why. I do not need to prove why each element of iota is true, because it is given to us. It is axiomatic. All right, so let me just kind of pause here and see if there are any questions regarding this statement here. Because this is the importance of iota, is we are given certain well-formed formulae that are known to be true. Don't ask me why, because we just know that they are true. So this is our starting point. All right, I'm seeing some questions coming up, so that's good. Okay, that means you guys are trying to process this. So they are said to be true. Yep, pretty much. So Eric is correct. So everything, each element of iota is known to be true, and that's it. Okay, you don't ask why. Typically, it is representing some truth in real world. As we'll, later on, maybe not today, I can give you guys some examples. So all elements of iota are true, and not all that are true are elements of iota. Okay, let me try to parse that sentence again. So all elements of iota are true, yes. And not all that are true are elements of iota. Not guaranteed, okay? Not guaranteed, because it really depends on what is in zeta in that case. If your zeta is empty, then everything that is known to be true is everything that is true. So if your zeta has a lot of flexibility, like, hey, if you look at these two things, and we can generate this thing here that is also going to be true, then you're talking about potentially, the set of all the well-formed formulae that are true may not be just the things in iota itself. So the significance of iota is it is the seed system to prove what is true. In other words, if I just give you a well-formed formula and I ask you, is this well-formed formula true? You look at that and go like, I know what to do with this. I'm just going to use it to match up with elements in iota. And then you come back and say, man, that sucks. Okay, this thing that you just gave me is not in iota. Well, just because it is not in iota doesn't mean it is not true, because we haven't talked about zeta yet. Zeta is how you can combine expressions. It's a pattern matching kind of thing, okay? If you pattern match this thing here, then that thing, that well-formed formula using components from what you just matched, is also known to be true, okay? So it's a way for us to basically label well-formed formulae to be true based on what is known to be true already. Alright, so can we add to iota? Nope, we do not add to iota. Iota typically is a finite set that is relatively small, and what we want to know is, using the rules in zeta, what else can we prove to be true? Let me see. Let me see what is the best way. We are running out of time, but I do want to wrap this up in a way where you guys can kind of conclude what we have talked about today. It's hard to say it, so I will try to explain it using a picture. Okay, so maybe just an example first. Okay, so I will conclude this class with an example of what we are going to throw in I. Okay, so it is possible that I may be a set where we can say 1 as a symbol is automatically true, or 1 as a well-formed formula is known to be true. The negation of 0 is known to be true, and then we'll say P implies right arrow Q is known to be true, and then we can say P. Okay, I can actually give you a whole system here. Q implies R is true. Okay, so I'll just kind of give you something this small. This is iota. Okay, so iota is not even touching ST as as well-formed formulae. It's saying is 1 as a symbol, as a well-formed formula is true. Not 0 is known to be true. P implies Q is known to be true. Q implies R is known to be true. So what is this, right? I mean, what is this saying? So now you can say, we can now map, what P is representing. Okay, so now we can say P is defined to be text classes are boring. So now we are binding actual real life conditions to the symbols that we are putting into the system. Now P is a variable. I'm not saying that my classes are boring or not. Okay, I'm simply saying it is a Boolean. Okay, it can be true, it can be false, but I'm not telling you whether it is true or not. So likewise, I can tell you what Q is saying is what Q means. Okay, so Q is so if text classes are boring, then at least one person falls asleep in text class. Okay. All right. So now you know what P means. You know what Q means. And what Iota is saying is it doesn't say anything about whether text classes are boring or not. It does not say anything about whether at least one person falls asleep in text classes or not. What it does say is if text classes are boring, then at least one person falls asleep in text class. So the conditional statement itself is given to be true, but it doesn't say anything about the precedent nor the consequent of the implication. Now you can add one more thing, right? So because it doesn't say anything about R, so we will say R is at least one person in text class feels refreshed after class. There we go. All right. So now we know individually what P is representing, what Q is representing, what R is representing. Iota, in this case, does not say a single thing about whether these individual pieces are true or not, but it does say something about the implications. So it is known to be true that this implication, P implies Q, is true. In other words, if text classes are actually boring, then we know at least one person falls asleep in text class. It is also known that this second implication is true. If at least one person falls asleep in text class, just think about 440 at the time for the time being, then at least one person in text class feels refreshed after class. So this does not confirm anything about P individually, Q individually, or R individually. It only confirms the implication itself. Now, I'm not going to go through the exercise today. So the question that I want you to think about is, so a question to be solved by propositional, I cannot spell proposition. Proposition, there we go. Propositional logic is P implies R. Is it true or not? That is why we have propositional logic. Okay, we start with something that is known to be true. We haven't talked about zeta because zeta is the key. Okay, zeta determines if you give me this is known to be true, if you give me this is known to be true, and there's a certain pattern to it, then we can label. Okay, I should say label. Then we can label a well-formed formula that makes use of the pattern being matched on one side, use it on the other side, and say that expression over there is also, I can label that to be true as well. So we can now start with whatever is in Iota, and then we can start to label additional well-formed formulae to also say, yeah, this is going to be true, and this is going to be true, this is going to be true, this is going to be true, and so on. So that is how we use propositional logic, is start with the language itself. Alpha and omega defines the language. Iota basically specifies the starting point, and then the most important piece that we haven't really talked about yet is zeta. Zeta basically says how do we spread it? Okay, since we are still okay, never mind. We're not in a pandemic anymore, but we are basically looking at how things can spread. Okay, these people have coronavirus, right? And then these people are going to be in touch with those people, and those people are going to be in touch with those people. So eventually, is that person over there going to get coronavirus? That's what propositional logic is trying to solve. So 1 is true, 0 is false, is no, 0 is not true. 0 is not, 0 is true. This is negation. This is not 0. But at this point, it's nothing more than a symbol. Okay, this is really just a well-formed formula. It is an expression that is syntactically correct, and I throw it into iota just so that we say, yeah, don't ask me why, but the negation of 0 is known to be true. That's how we define false, right? We can define false this way. All right. Sure, you can. It just won't be a system that is consistent with how people use those symbols. But sure, I mean, you can derive any system you want. So, I know we are running a little bit over time, but it is important to understand that you can define alpha, omega, zeta, and iota to be whatever you want. Okay, the only restriction is iota has to be a subset of all the set of all the well-formed formulae. That is one rule that you have to follow. But other than that, okay, you can define alpha and omega to be whatever you want, and out of all the well-formed formulae, just choose a few, throw it into iota. It would be a system. And once we talk about zeta, you can have zeta of any kind. The question is that system useful or not? In other words, does it actually reflect reasoning, logical reasoning? If it does not, then yes, you have a mechanical system, that can do pattern matching, and and it can label well-formed formulae to be true. But if it has no relation whatsoever to how we actually use logic to figure things out, then you have a mechanical system that is otherwise not very useful. So the objective is to figure out a system where we can define alpha, omega, iota, and then finally zeta, so that it does resemble how we reason things out, so that now we can have a computer system to do this mechanically. In other words, we are trying to get a computer to prove theorems for us. Okay, so that should make Mohammed happy, because Mohammed did not like proving theorems, and I cannot blame people for not liking to prove theorems, because it is difficult. Okay. So we want computers to help us prove theorems, and that's why this topic is in this class. So I will have one more thing. Yes, well, might as well just kind of round it up to 1:30 to end today's class. The reason why we want to do this is because we want to have a system where it can read your source code in C, C++, whatever, and it can prove that your code does what it is supposed to do. That is ultimately what we want to accomplish. Is we want a system that can go through your code or somebody else's code and mathematically prove that that piece of code is going to do what it is supposed to do. Because once we can do that, we don't need to throw test cases to a program to make sure that it does work anymore. We can just say, hey, we can mathematically prove this chunk of code is working, and that's the end of it. So that is the motivation of talking about theorem proving. And in this case, propositional logic is a fairly simple and primitive automated proving system kind of system, but it's easy to understand compared to predicate calculus, and is a good starting point. So I do want to give you this kind of background so that when you study, you kind of have an idea of why we are getting into this topic. So otherwise, I am done with the lecture. I'm just going to wait a little bit before I sign off to see what kind of question comes up. And then if you guys want to sign off, that's fine. It's still being recorded at this point. Alright, so Nathan said, so logically proven automation is one of our objectives of using this logic. That is correct. Let me do a quick Google search, and just to show you why it is important. Okay, so we'll look at automated theorem proving, and so this Wikipedia page will give you a lot more information. So typically you want to look into automated theorem proving, because your entire program, okay, when you write code, your program is can be seen as a transformation. So you have an initial condition, and then you have a desirable final condition, or final state condition. So the question is your program as a transformation actually going to take the initial state all the way to the desired final state? And that is a theorem. Okay, if you can have an automated system that can prove that theorem, then you don't have to throw test cases. You don't have to say, oh, does it work in this case? Does it work in this case? Does it work in this case? Because you have just mathematically proven that as long as your input meets a certain criteria, a set of criteria, and then your output is going to have certain properties as well. This is really important in computer security because not being able to do this is partially by a large margin, partially why we end up with vulnerabilities in systems, because they're basically just programs not doing what it is supposed to. So if you can prove your program is doing exactly what it's supposed to do, you can actually improve computer security tremendously. So this really ultimately connects to cybersecurity in a big way. Yeah, so we're going to continue this lecture. This is going to be a long module. I can tell you that, Danny. This is going to be a long module. So we are... Okay, let me show you how much we have gone through the module for now. And where's my mouse cursor? The problem of using a small mouse cursor on a really large screen is sometimes I can't find it. There we go. Alright, so in terms of the module, all we have done up to this point is, I would say, maybe about here. About here. Okay, this is about all we have done so far. So we have quite a few we have a lot of sections to go. And some of these are very difficult to understand until we kind of get a sense of what it is about. So we are going to be staying on this module for at least 2 more classes, if not more. That's a good idea. I like it when they leave a trail. I have not yet learned how to do it, but I have programmed my Windows key, because I'm using Linux, right? So the Windows key is kind of useless to do this. Okay, so that makes it easy to find. All right. So I'm just waiting for Mohammed and Nathan to finish typing before signing off, and then there's Luke. All right. Well, thank you. Thank you for being here. Oh, I got some ground loop thingy going on. Still haven't fixed the cable problem that I had. Yep, see you all on Wednesday. Yep, that's right. Alrighty. Yep, okay. So looks like we are done for today. Alright, I'll see you guys on Wednesday. But I will stay online for a little bit just in case someone has a question for me to answer.